Hello and welcome to another edition of Physics 264 Pre-Lab Tutorials. I'm Dr. Steve Brule. Today we're going to study the 55 timer chip. There are zillions of applications to the 555 and we're not going to go into really any of them. In our lab we're going to focus on how the 555 works. And as we explore this timer chip, we'll have an opportunity to exercise many of our skills that we've learned thus far in the course. Well, first let's look at the elements and operating principles of the 555. First, we've got a voltage divider right here. Won't talk too much about that. You know how those work. There we go. This is an RC charging and discharging circuit. You know how to do that from Physics 262. Op amps, there's two op amps working as comparators, comparing voltages at 2 points in our voltage divider. Well, what does a comparator do? A comparator is basically just an op amp, and if the positive, but it's not working in the normal mode that an op amp works in. It's working in a mode where if the it doesn't have any feedback. So if the positive terminal is greater than the negative terminal, say this was 1.1 volts and this is 1 volt, then the output goes all the way to the positive rail. And then if the positive terminal, let's say that was 0.9 volts and this is 1 volt, if this terminal drops below this terminal, then the output drops to the negative rail. In the case of the 555, we've got it hooked, we're operating this between plus 12 and 0 volts, and so when the op amp goes to the negative orientation, it goes to 0 volts. Okay. And then we have an RS flip-flop. You study those in your lecture class. A flip-flop is a binary device that has this truth table. Won't go too much into that right now. And finally, we're using a transistor working as a switch. Transistors are used in all of these elements. Well, not a resistor, but it's in an op amp and a RS flip-flop. They use transistors, and we haven't really talked about how they use them, but this is one application of a transistor is to use it as a switch. And when the transistor base, which is this part of the transistor, it goes high, then the current will conduct from the emitter to the collector. Okay, so that's all you need to know about the transistor switch. Well, here's our 555 timer circuit, and we're going to make our positive rail up here at 12 volts using the power supply we always use for our breadboards. This 3 resistor voltage divider divides this 12 volts into thirds. So at this point right here we have positive 8 volts, and at this pin right here we have 4 volts. So each one is a third of volts, and this is 12 volts, a third of the supply. Okay. So once we energize the 555, it begins charging this capacitor through RA and RB. So the current has to go through both of those resistors to charge that capacitor. The capacitor starts out at 0 volts, and when this is at 0 volts, let's take a look at the output of our comparators. So if this is 0 and this is 4, that's higher than this, so the output of the bottom comparator is high. And then this line also goes up to the positive input of the top comparator, and since 0 volts is lower than 8 volts, the output of that comparator is low. Then we can look at the truth table for our RS flip-flop, and we see that when R is 0, so that's low, and S is high, which means it's a 1 in binary terms, then the output Q is high. And the output of Q naught, that's just the opposite of Q, is going to be low, which means that this transistor will not conduct. So this path right here is just open, and it's like it's not even there. So the capacitor charges, and then when it gets past 4 volts, then it's going to change the output of that bottom comparator. Let's go back. See, it was high, and now it's going to go low once this point goes above 4. Does that change the output of our RS flip-flop? Well, now we've got a low and a low. We look at our truth table with low and a low, and we see that there's no change. So nothing happens at that point, even though this comparator is changing its state. We can see how long it took to get from this point to 1/3. This is at 4 volts. The time it takes to charge the capacitor from 0 to 1/3 of VCC. We just use the capacitor charging equation, and remember we're charging through both resistors, so that's 20K, and I get 0.8 of a millisecond to charge from here to here. Okay, so that's just getting the 555 started. So now, eventually, the voltage will become over 8 volts, which means that the output of that comparator is going to change, because now this used to be lower than 8 volts, and the output of this was low, but now once the instant it goes above 8 volts, the output of the top comparator goes high, and then we look over here to see when the R pin is high and the S pin is low, then we get the output goes low. So now it used to be high, now it's low. And yeah, so then now we're at this point right here, and then the capacitor starts discharging. But let's find out how long it took to get from here to here before we get any farther, and we'll talk about this discharging process in just a second. But let's find this time interval. So we're going to use the principle of subtraction to find this time. So first of all, the time to get from 0 to 2/3 of the voltage, which was 8 volts, that whole time is 2.2 seconds. So that was charging the capacitor up from 0 up to the 8 volts that we just talked about. And then we had already calculated the time it took to get from 0 to 4 volts. So this is 4 volts, this is 8 volts. That was 0.8 milliseconds. So using the principle of subtraction, this time right here is this time minus that time. Yes, very high level mathematical operation there. And so I just took the time that I get. It's really simple, but then when you look at it, it's kind of confusing maybe. So there's the time it took to get to 8 volts, and here's the time it took to get to 4 volts, and I just subtracted those two things, and then I ended up with this equation right here, which gave me, it says 1.8, it should have been 1.4 milliseconds. I have to change that. Okay, so that's our equation for the time it takes to go from here to here, and that's going to be important because we're going to have that charging from 4 to 8 volts over and over and over. This one only happens one time in the whole, just when you start it. Okay, so when this output went low, the output of the Q naught went high, which means it turned on that transistor switch, and once that happened, then this path right here goes to ground, and the capacitor starts discharging through RB. Oh, so then as the capacitor charges, it passes, it was at 8 volts, and now it passes, goes a little bit lower than 8 volts. And once that happens, then the output of this comparator goes low, but then once again we see low, low results in no change to the output of our RS flip-flop. So then the voltage on the capacitor drops below 4 volts. It changes the output of this capacitor, comparator, because now this is lower than this, and now this goes high. We look for when S is high and R is low, and we see the output of our RS flip-flop now goes high. And the wait a second, this is going low, which is turning off our transistor, so we stop discharging at that point, but we'll talk about that in a second. So let's find out how long it took to discharge the capacitor from 8 volts to 4 volts. As far as this is a little bit tricky, as far as the capacitor is concerned, once it starts discharging, it thinks that its top voltage becomes V0. V0 becomes 8 volts now instead of 12 volts, because as far as the capacitor is concerned, it starts at 8 and now it's discharging from that value. So I use, oh, and it's going to discharge from 8 volts to 4 volts. So that means that it's going from V naught, which was 8, to 1/2 V naught, which is now 4. So it's not going from 2/3 V naught to 1/3 because V naught changes as it is discharging. So here's the equation that we get for discharging, and note that the discharging takes place only through RB. Let's look back at that. See, as it discharges, it only goes through that resistor. Okay, and then I get 0.7 milliseconds for this discharging. And we already talked about how the RS flip-flop turns off our transistor switch. And then the whole process starts all over again. It starts charging now. Instead of from 0, now it's going to start charging from just below 4 volts up to 8 volts. So this process where it charges up to 8 volts, discharges down to 4 volts, charges up to 8 volts, discharges to 4 volts. That goes over and over and over again. And then the output of the 555 looks like that. It's a square wave that has a lower amount of time at the low end and a higher amount of time at the high end. Okay, so the period of our oscillation, which is one of these cycles right here, is just we add this 1.4 milliseconds and the 0.7 milliseconds, and we get 2.1 milliseconds for the R and C that we have chosen. Okay, nothing fancy about that. Well, let's assemble our 555 test circuit. First of all, we start with the 555, and I'm just going to go through all the pins one by one and hook them up. So first of all, pin 1 goes to ground, so there's pin 1 going to ground. Pin 8 goes to the positive voltage rail, which in our case is 12 volts up here. The pin 4, and I'm putting a little check for every one that I get done so I can keep track of what I've done. Pin 4, which is 1, 2, 3, 4, this pin right here, is also connected to the positive rail, and I just did it with a jumper over to pin 8 because pin 8 was already connected to the positive rail. The capacitor goes one end to the ground and one end over to RB, so I just start with my capacitor right there with one end to ground. Then I connect RB from one end of the capacitor to right here, which I'm going to connect to it's going in the opposite direction as it shows here. So there's RB I've just hooked. Now let's hook up RA. RA goes from one end of RB up to the positive supply rail. So I connected it to that pin 8. We could have taken that resistor and just connected it right here to the positive supply rail, and it might have looked a little slicker that way. Pin 7 is connected at the junction between RA and RB. So right here is the junction between RA and RB, and I connect that with a little jumper over to pin 7 with that white wire. Pin 6 is connected to pin 2, so here's pin 6. I ran a yellow jumper wire over to pin 2. I never would use black. Look at that. Somebody used yellow up there for our plus 5 volts. Well, oh well. I would never use red, blue, or black for one of my jumpers. Pin 2 goes to the junction between the capacitor and RB. There's the junction between capacitor and RB. And there is pin... Oh, look how I did it. I didn't want to... I moved it over to here. It looks like it's going to pin 5, but pin 5 is already connected... 6, I'm sorry, it's pin 6. Pin 6 is already connected to pin 2, so then I just connected it over to pin 6, and then which is already connected to pin 2. So there was a little detour there, but that's how I did it to make it a little bit cleaner looking. Okay, and then so that gives us everything, and then we just connect this outboard connector right here to pin 3, which is right here, and that's the output of our 555 timer. Caution! And this happened last lab, and a lot of people got bad data because of this. This knob is the knob. If this knob is not in the calibrated position, then every time measurement that you make on your oscilloscope is garbage. It means that whatever your time-based scale is saying is not really what the oscilloscope is showing. That knob is just used to get a sort of qualitative look. So if we wanted to expand this out and make it so it filled the whole screen and we didn't care about making any measurements, then we'd turn this knob. If it was up to me for an educational oscilloscope, I would not even have that switch because it messes students up so many times. But make sure that that is in the calibrated position. Okay, well, now we're on step 4. We're going to vary the power supply voltage on our 555 timer. So first of all, we need to get our power supply handy there, and I'm hanging that over because once this oscilloscope is tilted, and if you put your power supply just on it without hanging it over like this, it could slide off, and wouldn't that be embarrassing? So let's get rid of the power connection that we had to our 555. After we're going to undo that, of course. And instead, we're going to use this outboard connector to use our external power supply to power our chip. So now we can put whatever voltage we want to power this 555 timer and see what the output looks like with different power voltages. Okay, make sure that this knob on your external power supply is all the way up so that your current is not limited. So if you turned it this way, it would be a way of limiting the current to your your 555, and you don't want to do that. Okay, so this is the knob you'll use to change the voltage and make your observations. Step 5, sketching the capacitor voltage along with the 555 output. So now this pin 3 was going to your oscilloscope before, but now we're going to make another connection using this outboard connection to the capacitor voltage. So there's the capacitor voltage between was that RB and the capacitor. So I just made a little tap right there between those 2 points. And before you start this up, make sure that you zero out your voltages on your dual trace. You set the you set your oscilloscope mode to dual trace, and then make sure that both of those voltages are zeroed so that you'll have, and I just put the one for the, this is going to be the capacitor charging, and I set that to 5 here. So now I'll see how the capacitor charging looks down here, and then this is the output of the 555, and I've got its 0 point down a little bit because it jumps up pretty high, and if I had it up here, it would jump off of my screen. So your dual trace, once you look at the charging and discharging of your capacitor along with the output of your 555, should look something like this, and you'll make some observations, you'll measure this period and so forth. Step 6, short RB and observe what happens. So remember, RB is that's Dr. Brul's dog in the background moaning because she wants her food. So as the capacitor is charging, it goes through, the current goes through RA and RB, but then when the capacitor is discharging, it only goes through RB. Oh, that's what I already showed you here. So it's charging, going through both of them. When it's discharging, it only goes through RB. And so what we're going to do is short this resistor. And when you are shorting a resistor, it's essentially, you might as well take that out. Well, you're not going to have to take it out because the current just bypasses that resistor. It'll go, the current will bypass that because this is a path of zero resistance, which it would rather go through than going through a resistor. So that's called shorting a resistor. So it's essentially taking this resistor and replacing it with a wire. So when it's discharging, look at that, it's going to make the discharging time very small because the RC time constant, well, with R0, there you go. And then when it's charging, it's going to make it smaller, but not that much smaller. It's just going to be half as much because you're only removing one of the resistors when it's charging. Caution, do not short RA. If you do that, you will, if RA is shorted, then when the transistor turns on, then there's no resistor there to limit the current through your transistor, and it will blow that transistor and make your 555 timer garbage. Okay, step 7, diode in parallel with RB. So now instead of just shorting RB, we're going to put a diode in parallel with RB. So while that capacitor is charging, the diode is forward biased, and then it acts like a short across this resistor. So the charging time is a little bit shorter, well, half as short, as long as it was with both of the resistors. Then when it's discharging, then the diode acts as an open circuit, so then RB comes back into, so that it's as though that wasn't even there. So now your discharging path goes through RB. And here's a picture of the diode actually in the circuit in the forward biased mode, where the line of the diode is pointing towards the capacitor. And you're going to make your observations and see what the output of the 555 as well as the capacitor looks like. And I think this is the final step, changing the top comparator reference voltage at pin 5. So let's remove that diode from the circuit, and now we want to be able to look at the voltage on the capacitor and the output of our 555 at the same time, going to our dual trace scope here. So these two lines are still going to the scope, but we need another external connector so that we can connect pin 5 to our external power supply. And the way you're going to do that is put a alligator clip on the end of a banana connector wire, and then connect that to a wire which will then go to pin 5 of your 555 timer. By changing the voltage at this is the control voltage, and we're changing the voltage at this point, this negative input of the top comparator, we can change it to any voltage we want. This is 12 volts, remember, but now if you put this at 11 volts, you could have it at 11 or 1 or whatever you want. And now it's just, there's going to be some current that flows through here, but who cares? That's just going to the power supply. So now this will be whatever you place it at using your external power supply. And then now the only resistors that are important are these two, and this becomes a voltage divider, which just takes your voltage in half now. So if you had this voltage, say, at 10, then the voltage at this positive pin is going to be at 5. So put together all of your imagination and try to imagine how changing that voltage, the voltage here, and which in turn also changes the voltage there, how is that going to change your output of your capacitor and your 555? Thanks so much. We hope you've enjoyed the show.